Hello, my name is Kai,
And my name is Jack.
and this is our statics project.
Oh yeah.
Our overall goal here is to find out the internal forces on a ratchet and a ratcheting mechanism. So the way we've achieved that is this contraption here where we've rigged up two ratchet straps, one that we're actually testing on and one down here that we're providing tension with. In between the two ratchets we have a load cell. That way we can get an accurate measurement as to how much tension we're putting in the line. Both are tied off on solid ends, so there's little to no deflection in the actual ratchet. And then down here we've tied it to a base to keep it level and help our measurements come out. Here we've added a moment arm where we can measure how much weight we're adding to help determine the force that's in the gear that's holding the ratchet in place. Yeah, there might be 200 pounds of tension in the line. How much is actually held at the gear here? So that's what we're trying to figure out today, and we're gonna do an example real quick, and then we're gonna continue to get our measurements this way, and then we're gonna go to the classroom and do some math and figure out how it all relates. So first we're gonna tension up the line. So while we wait for this to come down, the reason we're waiting is as we actually tension the ratchet, there's a lot of little movement, contortion and tension in the line that likes to move and shimmy a little bit. So we want it to settle down before we get our measurement. That way we can try to be as accurate as possible. So it's still decreasing. So we'll see what it is here in a second. So right now we're at 167.4, and we just dropped to 166.6. So we're wanting it, as I said, to level out to get the best measurement. So here we go, we're at 165.4, and it looks like it's leveled out a lot. So now we are going to add our weights to the arm here and see how much it takes for this to start to move. We've done some previous tests already at, what did we do, 160 pounds or something.
Last highest was 164. So
We need to do more. We can do this, right?
yeah.
All right, so we'll start with, what do you say, 5 pounds?
5 pounds sounds good.
So now at this point, we're gonna continue to add weight until we can see that lever move off the ratcheting tube. Let's add this one. Okay, so
Deflecting.
yeah, it's moving now right off of the gear.
All right.
So this is what we're going to use as our measurement. So we're going to take all these weights off, and because they're in a variety of metric and standard units, we're going to weigh them on the scale to get a concise measurement.
All right, this is part 2 of Jack and Kai's Statics MBT 111 project video. All right, so we start off, we took an overall free body diagram of the entire ratchet. We included all the external forces on it. Those are the 2 tensions from the 2 ends pulling it, the weight pulling down, and the tension of the screw we used, well, the force from the screw we used to grab it, pushing up, causing this thing to be static equilibrium, not moving or accelerating. Also in free body diagram 1, we went and added all the dimensions of the math, so we wouldn't necessarily need to add it to the other free body diagrams, even though we did in some cases. So here, free body diagram 2 is of the back section of the ratchet. We have T2 from the back strap pushing out, D from the screw grounding it, pushing up, and then we have internal forces. These are the forces from the gear tooth, right here, and the little metal section stopping the ratchet from rotating, right here. We have R, and gear tooth and named C. This angle theta here is the same angle theta right here. It is 13 degrees, and that theta was necessary for all the calculations determining R and C. Over here, free body diagram number 3, we have the weight, the force at point B counteracting the weight, and the moment about point B counteracting the rotation that would be caused. And right here, free body diagram 4, we have T1, as well as the equal and opposite forces and moments from all these separate internal forces, keeping the whole thing static equilibrium. Over here, the beautiful math. We trivially from the free body diagram 1, we can determine that the weight equals D and T1 equals T2. It's not that complicated. And then by some moments at point B, which T2 passes through, so it could be ignored, we can mathematically determine the ratio between the weight and the tension, which is, the weight is approximately 5% of the tension, it's a little bit more. Then we moved on to free body diagram 3. Trivially from that we can determine the weight equals By. It's not really the interesting part. The interesting part is calculating the moment to point B, which equals the weight times its moment arm. Moving on to free body diagram 4, we took some moment at point B, used that to determine the force at C. Now going over here, can't really see it well because we drew with our own hands, but C is tangent to the circle, and R is directly pointing into the circle. So R passes through point B, therefore it has no moment arm, so some moment arm at B would counteract that. And because C is tangent, it's just trivially R times C for its moment. So it's pretty easy to calculate. From that we determined mathematically what C would be, this love formula right here. We went down, then summed forces in the X direction, and rearranged it to figure out what R is, and of course theta is 13 degrees, and we measured that by hand. Now, what was the result of all this? Well, this right here is our beautiful math. So beginning, we have the weights. WA equals the actually measured weight. WT equals the theoretical weight. As you can see, the actual weight was slightly higher than theoretical weight, with the percent difference between them slowly rising as more weight was added. We believe that they all go into the reasons for differences later. Anyway, we have the measured tension, because we measure the tension using the strain gauge, I believe, that's what it's called. And then we just use that real tension to put it in the formula to get the theoretical values, so there's only one tension. We have calculated what R and C should be actually using our real values, what they should be theoretically using our mathematically calculated values, and then we've calculated percent difference between them. So as you can see, when it comes to R, percent differences are less than 2% and often less than 1%. So our values for R, pretty spot on. Our values for W are between 14 and 20%. We would like it to be lower, but still, when all the factors that I'll mention later come up, it's understandable why that is. And coming over here, the percent difference for C is quite substantial. It starts off pretty low, like 12, 14%, not bad. And then it quickly jumps up to 42%, which is pretty bad. But there are several reasons for these. These reasons for the percent differences are pretty simple. First off, we neglected the weight of the actual body. When we come to the ratchet here, we only calculated the weight on this end. However, our lever arm had weight, and the entire body itself had weight, which would make this weight larger, as well as move the center of gravity to probably somewhere closer to like here, which would throw our calculations way off. We neglected the friction, as the ratchet strap was wrapped around this several times, generating a lot of rope friction, which would of course oppose it, making our horizontal values slightly different. And finally, we did this test outside where wind was present. While it was not particularly windy, there was still wind, which would move it back and forth slightly, which would change the values. And of course, there's all the friction from the internal parts rubbing up against each other, which would throw off our values slightly as well. But overall, we're confident that we have successfully analyzed the internal and external forces onto this system.